Hello everyone, this is a presentation about MutateNN, which is a mutation testing tool for deep neural networks deployed on different hardware accelerators. The tool is available on GitHub and essentially it's a configuration-based utility that allows us to compile deep neural network models, generate mutants of them and also compile the mutants, perform inference, execution of the deep neural network models, and we can do it on each of the different devices that it's going to be deployed. We can deploy them on different devices, and eventually it can analyze and compare the results. So the tool consists of it's a Python-based utility, but it's implemented in Python. And what it's, as I mentioned before, it's configuration-based, which means that we can define the model, we can define a number of settings, but most of all, we can define where we will focus on three settings: build, execute, and evaluate for each one of the models. And what we can do is we can set the settings of the model, such as the original O and next we can import it, and or we can import it from the pre-trained models of deep neural network frameworks such as PyTorch and Keras. And once we have our model, we can set a number of mutants. Our tool supports a handful of different mutations. For instance, we can go into the end code, the compile code, and mutate the less than operators in conditional statements to less than equal, or we can go to the graph of the model and transpose, for instance, a data tensor or a weights and biases tensor. Here in this mutation, it's going to transpose the tensor, the input tensor, the data tensor for convolutional operators. And now that we have defined our mutants, for the sake of simplicity and for our example, we're going to perform the transposition mutant and the less than to less than equal, but our tool supports much more um, mutations. We have defined our mutant, and the next step is we can set the device that it's going to run on. For now, we're going to perform the execution of the model, the deployment and execution of the model on the default setting, which is our local device, which is it consists of an Intel-based GPU. So now that we have all settings, we can enable build to true as it is here, and we can run our tool. We can run MutateNN, and as you can see, our tool is going to compile the original model and the mutants. It has compiled the original model. Now it compiles the transposition mutant. And now it compiles the less than to less than equal mutant. And now our tool completed the compilation operation. So if we go in our in MutateNN, we can go to the models, the generated models, and we can see that our tool has generated a number of files. The tar files are the compiled models that can be imported into Apache TVM. Our tool is built on top of Apache TVM, which is a well-established machine learning compiler that allows optimization and code compilation to be deployed on a number of different hardware acceleration devices. And now that we have our models ready for further usage, we can deploy them and execute them. So are going to switch the build setting to false, and we're going to set the execution setting to true. And what this is going to do is it's going to take each one of our mutants and it's going to deploy and execute them, perform execution of each one of the original model and the mutants on the local device. And it's going to perform inference for a whole data set that we define. So we have defined we have defined the number of datasets which are contained in folders. We're going to select the small dataset which consists uh, of just a small amount of images, and we're going to perform the execution. So we have selected our dataset, we have set our setting for execution, so we're going now to perform the run. And MutateNN is going to take each one, the original model for our the original variant of our model, and the mutants, and it's going to perform inference for each one of the images of the dataset. So it takes a little bit of time in order to prepare everything and perform the inference. But as we see here, it performs the inference for each one of the mutants for the whole data set. And if we go back into the files in MutateNN, we can see now that we have a run. So we have, this is our device. And we can see that we have some folders that correspond to the original model and the mutants. And if we go into one of the mutant, we can see we have a number of folders that correspond to the timestamps of different runs. So let's go to the latest one. And we can see that for each one of the images in the dataset, we have an output file that practically contains the top 5 predictions for this file. This is an image about a drum, and our model is pre-trained on ImageNet, so we're going to take the IDs for the ImageNet labels. 541 corresponds to drums. And here we can see the execution time and, of course, the certainty of the model near each one of the predictions, the prediction IDs. So now that we have the executions, of course, this is done, the outputs, I mean, of course, this is done for the original model as well and each one of the mutants, as you can see here. Now that we have them, we are able to perform analysis. And we have run already before a number of different devices. We have our local, but we also have 3 more devices. So what we're going to do now is we're going to enable the analysis module of our tool of MutateNN. And as we do so, we will allow the tool to perform pairwise comparison. And as we see, it has generated a number of different files. And what it does, it performs comparison across devices. But of course, if we also go into a device, we can see that we have comparison across the original model and the mutants. So if I open this file, we can see that we have a comparison of the original model against the mutant, less than to less than equal. And we can see that for this particular case, we have 100% similarity across all 5 images of the dataset. And of course, we have more metadata such as execution times, etc. So of course, for this small dataset, we had no discrepancies for our local device against the original. But if we go to another device, this might not be true. For instance, if we go to this device, you can see that the less than to less than equal had a 60% similarity against the original model. So now that we have this, we can compare each mutant against the original model outputs. This is one part of the analysis. And the second part of the analysis is that the tool can practically perform evaluation across devices. So it can evaluate the output of devices, and it can compare the outputs, and it's mutant oriented. So it can go for less than to less than equal mutant and say that device 1 and local, they had no differences. They had all images similar. However, if I go down, you can see, for instance, that for device 3 and against device 1, there was a difference in percentage. There was only a 60% similarity. In that way, we can compare our results both across the original model and the mutants, but also against devices for each one of the mutants and perform pairwise comparison for each one of the devices. So, as I mentioned in the beginning, the tool is available on GitHub, and it allows the import of ONNX models, but one can also define file-based models such as um, it can define other file-based models. For instance, you can import a model from a TensorFlow graph, but also default versions and models that are already provided as pre-trained models from deep learning frameworks such as Keras and PyTorch. This pretty much concludes the presentation of our tool. I want to thank you for your time, and I wish you all the best.